a kind of general love for the particular. So if we talk about computers and historical linguistics, the first thing that kind of comes to your mind in general for people who have heard anything about it is a paradigm like this. So what I call tree crunching. So like you ask specialists of a language group with a already mature tradition of historical linguistics, and you ask them to encode tradition to a couple of binary trees, whether this language had this or not, whether this word in this language is cognate to that word to that language or not, and you just put it all into a kind of phylogenetic algorithm, and you get a tree. And yeah, that's nice, but I don't think that's the thing that's the most appealing to historical linguists, because I put my basic misgivings to this kind of paradigm in three subtitles. So first, it's the kind of the inverse, because in general, computers are supposed to help us doing things, but now computer is going to run an algorithm, and we encode things so that computers can read them easily. That's not the happiest thing ever. The second thing is this kind of big conclusionism, which is why I begin my talk with a nod to our host, which is that the idea that, you know, historical linguistics is not an end to itself, but a means to a tree, which can be compared with genetic trees or large historical movements of people, things like that. Of course, those things are extremely interesting. I think everyone spend some time listening to crackpot series about this kind of things, but that's not actually makes historical linguists fun for us, and that's not makes our fruits of labor useful for people who speak their languages or who identify ancestrally or regionally with those languages. And the third thing is that it relies on traditions for language groups that already had a tradition. So it doesn't produce anything new for us. So how about having it the way around? So let's have computers in service of human beings, and let's have computers to help us create and perfect hypotheses that are classical, that actually interest us, and that are concrete on this specific trait of this specific language or language group. And also we want to have, and also we wanted to work in a sort of exploratory context, so that computers help us to create new traditions, to bring rigorous historical linguistics to places, to language families where it didn't exist before. Okay, so the idea of CAPR is that of a reconstruction assistant. So like, what's a word processor? Well, that's what you use to write documents. So that like the documents exist inside the word processor, and by interacting with a word processor, you write your documents. Okay, so CAD is used for technical drawings or designs, and a proof assistant in mathematics is used to create computer verified formal proofs. So that's the basic idea of a reconstruction assistant. So the linguist or the linguists interact with this reconstruction assistant, and it as software, it takes a bunch of input, which is basically the lexica of daughter languages, and you gradually elaborate. The assistant helps you to elaborate the linguistic reconstruction, your hypothesis about the history of this language group. and at a certain point, when you think that the thing is good enough, it can be output into a kind of an etymological dictionary or other kinds of handbooks of the language group. Okay, let's say that historical linguistics is not like the hardest problem ever for computers. I mean, a lot of historical linguistics is just a string search and replace. A lot of other things are just statistics. So in principle, we should be using computers everywhere. But of course, that's not what happened. And yeah, we basically use computers as word processors, and yeah, so with maybe some custom Ruby scripts or Ruby scripts or Excel magic to get something done, but it's not computational. And we have recently a couple of great surveys on the computational and computerized methods, and like for every single subtask, for every single step in the general workflow of historical linguistics, you actually get very, very good computational and computerized methods. So what do we need? Well, let's say the technology is already here, and what is needed is engineering. So you just need to, when you have a context, like when you actually want to do something, and you also actually want to involve computers in the thing and see what we can create. So that's the basic idea. Okay, so let's talk about some of the previous approaches, and from an engineering point of view, which is to say, how can it be made to produce concrete results of a good quality? So let's focus on one of the most important tasks when we consider historical comparative linguistics, which is that of cognate assignment or cognate determination or cognacy, whatever. So you have a bunch of words in different languages, and you try to partition them into different cognate sets. So this word is cognate to that word, so you put them all together and you call it a cognate set. I call it cog set, but it's this. So there are two basic computational approaches to cognate assignment. The first one is automatic cognate detection. So basically it's an algorithm, which is quantitative, kind of language agnostic. You just give it an input, the word list, and it tells you which word is cognate with which. That's the first idea. The second idea is that of back projection etymology. So basically you have already the phonological history of the language group pretty well, and you encode them into, let's call them programs that reconstruct the every daughter language form into a proto-language form, and you kind of crisscross, you triangulate the results together and see what can be fit into cognates with what others. So automatic cognate detection has a very long history. The earliest approaches are actually pre-computer, like you devise a kind of method for 3 or 4 research assistants. They still had research assistants at the area, and you have them crunch words like a computer in a certain manner, so you can gain a rough first idea of what kind of cognates can exist. So as soon as the thing gets computerized and have some actual engineering constraints, The basic methods rely on actual phonetic similarity, which is like kind of a no-no to historical linguistics, for historical linguists, because yeah, this kind of thing that basically you have, in Persian, bad means bad. So yeah, Persian bad is cognate to English bad. Of course, the world doesn't work like this, but those algorithms will pick up those coincidental lookalikes while fail on non-obvious cognates. So what we actually use here is this method developed by Johann Matthias List called lexica, which uses a pairwise sequence alignment to closely mimic the behavior of comparative method. Basically, it takes words, like assume that words that might be cognate are actually cognate. So you get a kind of score of correspondence, and you use the correspondence score computed from the word list itself to determine the, so it's a self-referencing, it's very robust, and it's most importantly, it fixes this problem of over-reliance on the actual sound value, and it has a robust independent behavior. So yeah, the algorithms, especially the new ones like Lex, that are great. So if you use it on some kind of German, English, Dutch, French thing, it gives 95% accuracy, but it cannot function as a whole workflow by itself. So the question is, what happens afterwards? If you get a bunch of cogsets, how are you supposed to correct them? So this problem itself has like two dimensions. The first thing is, of course, our idea that we want to explore new language groups. So when you develop an algorithm, you think that like there are trained specialists who have this magical power to tell the true cognate from the false, but this magical power is downstream to a very, very mature tradition of historical linguistics. So yeah, so basically, if we don't think very deeply about those kind of problems, you're basically having computers helping people to do things that people can already do, but cannot help people doing things that they don't. And the second stuff is what I will call the Chinese typewriter problem. So even with linguistic expertise, it's quite non-trivial to think of a way to correct cognitive judgments. This is a very logical kind of inventory of cognitive judgment errors. So overlumping, oversplitting, and misattribution. I think I tried to talk in like overcorrection or type 1, type 2 errors, but it doesn't work like this. So, okay, overlumping is that if the ground truth has like those 3 cognate sets, but in fact, algorithms tell you that they all belong to one cogset, and oversplitting and misattribution. So for overlumping, you need to split one cognate set into several. For oversplitting, you need to merge several cogsets together. And for misattribution, you need to move stuff around, move stuff between cogsets. Okay, that's the problem. So if you have this, of course, you know that, okay, here are 2 blues thingy you need to put here, and here is one red thingy you need to put here. But, human beings don't have like infinite memory. So basically, if you put those things like physically, visually adjacent, juxtaposed to each other, it's very easy to see the pattern. But the problem is that, like, if you actually run the lexica algorithm or any kind of algorithm on the actual data, you get you get a huge bunch of cogsets, and it's just not feasible to reassign forms to do this, but across 3,000 or 10,000 or more cogsets. So here's a perfect analogy. So I once, so I took this picture at one of the libraries in Heidelberg, and yeah, this is this marvelous machine called the Chinese typewriter. So apparently you have a kind of mechanical cursor, and you need to locate this mechanical cursor on one of the characters, and you use the button, and it moves this type to the paper to produce characters. Okay, so imagine this, but like every type is a cogset which contains huge bunch of words, and you need to match this cogset here to this cogset here, and while looking at all those, no, it simply isn't going to work. Okay, so as a conclusion, so automatic cognate detection is a great. It generates excellent first drafts of cognate assignment, but there's no obvious way for human linguists to correct the result. Okay, let's talk about the second idea that is very crucial to the development of the CAPR methodology. So here's what I call back projection etymological dictionaries, or in short, back projection etymology. So what's the idea? So, okay, it's the idea of Xun, who in, I think it was in the 70s, who had this brilliant idea of producing a computer-generated etymological dictionary of Algonquian languages. And here's a sample entry from that dictionary. So if you can see, yeah, it's you have the Proto-Algonquian word with Cree, fox, Menominee, or Ojibwe, and how do you compile how can you make this kind of dictionary with a computer? Well, so Algonquian is one of the language groups that has an extremely developed tradition of historical linguistics. So like I think back in 20s or 30s, people yeah, understand how the sound changes very well. Even for quite difficult language like Menominee. And so what happens is that you can, since you know the historical phonology almost perfectly, you can write programs that back projects. So what's back project? So yeah, you take, it's a function that takes an actual daughter language form and produces the list of possible proto-language forms. Okay, you have a back projection, and so you can have computer just go through all the daughter language dictionaries and yeah, unite them, see if this one can be reconciled with that one in terms of proto-language form. So it's from an engineering point of view, it has the unique distinction of actually working. So yeah, here is the dictionary. And why it works is also kind of easy to explain, because when you have like those three kinds of cognitive judgment errors, okay, so basically you just need to yeah, get rid of basically homophones, which is overlumping, and it doesn't require this kind of matching things together in 3,000 or 30,000 item set. Okay. So the problem isn't actually what happens afterwards, because because you just need to split cogsets that are already made, so it's easy afterward. The problem lies before. So it has a kind of, let's say, fragile dependency on a perfect historical phonology. So let's get that into a kind of, I think, exaggerated example. So if you just have a group and you write some rules and which are quite wrong, and yeah, it compares everything and it gets you 50 etyma. 15 etyma, and yeah, you have your great etymological dictionary of group X that has 15 etyma, and you have absolutely no idea what went wrong, because it doesn't give you, when it fails gracefully. You just have no idea. So it works only in this very limited context of like scaling up a reliable theory of historical phonology to an etymological dictionary. And but we are trying to do something else, which is this exploratory stuff. When you have a group that you don't really know about, then what you can do about it. Okay, so while for the algorithms, the challenge lies in how can you find a way to correct the results. Here, the challenge lies in the need to have a way for linguists to discover and gradually refine the historical phonology. Okay, so that's the basic idea. So yeah, for both, if we look at them like from this kind of engineering workflow point of view, they both have this fatal disadvantage of being non-exploratory, non-iterative. So yeah, you need to already have a perfect knowledge of the group you're working on before you can enlist the help of computer into it. And of course, if you know the group perfectly, why do you need a computer? Okay, so let's distill this discussion into the design goals. So in order to have something that we actually would want to use, the first goal is what I call optimal human-computer cooperation. So the ideal is to have the computer working like some kind of very intelligent, earnest assistant, or more like the student and you're the director, and yeah, the student does everything to their ability, but then ask you, okay, so how can I get this? So you get to generate the, so you do the interesting bits, generating hypotheses, giving intuitive judgments, and computers do the work like enforcing consistency, keeping track of details, and crunching dictionaries. That's the ideal. And the second design goal is incremental improvement. So yeah, so as we have seen for the kind of back projecting etymology thing, so it really needs a good hypothesis of historical phonology, and so which in most cases we don't have. So yeah, a good system should encourage hypotheses to be gradually built and refined. A crude set of hypotheses should still reward the linguist with more and better information, so that the linguist can later use those new information gained from the bad hypothesis to make a good hypothesis. And here is a third thing, which is a non-destructiveness. So yeah, basically, you need to think really hard so that if the human linguist does something, then yeah, it shouldn't be thrown away except when the human linguists themselves think the thing is wrong. Okay, so yeah, let's talk about our workflow, which is this thing called CAPR, computer-assisted proto-language reconstruction. So the context is that we in this framework of the ERC project Beyond Boundaries, and we want to do an etymological dictionary of Burmese languages. Okay, so we have a lot of digitalized data, and but now, yeah, we're working on this, working on just finding a way to gracefully let us make a first version of the dictionary, I think, from the 6 languages in a certain parallel lexical kind of source. Okay, the context is that of monosyllabic languages. So, okay, okay, so some people think that monosyllabic languages means that most of the words in those languages are monosyllabic, which doesn't exist, which doesn't really exist, I think. But it's still a very important kind of typological type. So yeah, the morphology is mostly compositional, and the productive morpheme boundary coincides with a syllable boundary. And also, so there's little that happens between syllables, either diachronically or synchronically. So with monosyllabic languages, basically it kind of allows us to forget about words and take syllables as the basic unit of phonological evolution and etymologization. So yeah, here's an example of the cognate sets for monosyllabic languages. So, for example, brain in Maro is basically head brain, and head hair is head hair. So all those and this word hair is like a flesh hair. So this head thing goes here, this in brain goes here, and the head hair thing also goes here, while the second syllable is going to be etymologized on its own in another coxet. That's the basic idea of monosyllabic languages. It saves us a lot of work. And yeah, so CAPR is developed for monosyllabic languages with its limitations. So later, if we're going to make it more useful for other kinds of languages, we need to think more about it. So the actual document, the CAPR workflow allows us to work on is what I call the bipartite hypothesis, which is made of 2 parts. So you have the coxes and you have the phonological history. So, okay, the coxes are the coxets. So a word in the general case or a syllable in this monosyllabic case belongs to a coxet, nothing fancy here. And the other thing is what we call phonological history. So basically, yeah, you write them in as finite-state transducers in the firmware language. So I don't have time to talk about how great transducers are today, but basically it's the idea is that it gets you to write historical evolution in SPE style, which everybody kind of knows. And also automatically permits you to project forwards and project backwards. So yeah, that's what we need. So first, so the phonological history is actually composed of 2 parts. So we're looking at this example where Proto-Burmese ba gives Ngochang bo. So first, you need to define what a legal syllable in the proto-language is. So, for example, here, the legal syllable is composed of the initial and the rhyme, and the initials are those, and the rhyme are R and E. So you see that ba, B fits in the initial here, and R fits in the rhyme here. Nothing fancy. Then we need to define the individual sound changes that lead from the proto-language to Ngochang. So for example, here's a rule of devoicing, which turns B into P. And here is a rule that turns R into O, so that we get bo from ba. And finally, we have this transducer called Ngochang, which defines not any legal Ngochang syllable, but like a perfectly inherited Ngochang syllable, which is lautgesetzlich derived from Proto-Böhmisch, excluding loans, analogy, and other shenanigans. So yeah, so how do you define it? Well, you take the actual proto-syllable, you take the proto-phonotactics, and you apply the sound changes one by one on it. So first you apply the devoicing, then you apply R to O. And so here you get essentially an ordered list of sound changes applied to the proto-language syllable. An interesting point of the CAPR view of hypothesis, or the data on which the theory on which you actually work on, is that you don't actually do any protoforms. So I mean, if you take a look here, you might think that, well, the linguists need to write glottal stop O and H for the head. No, it shouldn't work like this, because basically the protoforms should not be provided by the human linguist, but inferred from the phonological history and the daughter language form. So we get a toy example here. It means tears. And yeah, so this word reconstructs in Achang AOC, reconstructs to, sorry, this word B reconstructs to all those different proto-Böhmisch syllables, and this word reconstructs to all those, and this word reconstructs to all those. So you do some kind of set theory operation. In fact, it doesn't always work. So yeah, some kind of complex heuristics to tell that the actual reconstruction of the whole coxet is likely to be B. Okay, that's how it's supposed to work. So why do we do this? Because it permits a kind of rapid iteration of phonological history. So if you do any kind of reconstruction, like on hand, one of the not very thorny but very annoying problem is this kind of thing. So like if you change your hypothesis, and so if you change your proto-language phonotactics, and every time you do such a change, a lot of the proto-language forms need to be replaced. And so, yeah, basically we just get lazy and like never update your reconstruction, except when you have like a complete new vision of how things are supposed to work. And then, you know, this kind of things, which are still quite counterproductive, because I think, and we will see later, that actually the best way to make good reconstruction, to make good hypothesis, is to iterate very quickly on the whole theory. And so we got transducers, we got this phonological history, and what are they used for? Well, the first insight of the CAPR methodology is that you just blindly do a backward projection whenever possible, and very often forward projection, and that provides a lot of context to the linguist. So for example, we get this word here, cloudy. So yeah, the inferred reconstruction is zu x. So in this for the RC word mao zao, for example, the syllable zao is yeah, the computer runs the transducer backwards to do a projection from zao, and it sees that it is reconstructed as zu x, so it accords, it is harmonious, it conforms with the projected reconstruction of the whole cockset. So you get a tick here, and you get different kinds of crosses. So here's a kind of crosses. So for example, Mao Zhao, and Zhao, at least according to our current hypothesis, it can only come from Zhu, not Zhu. So here it reconstructs this word back, it produces Zhu, and tells you that, well, it does have a reconstruction, but it's not a reconstruction that conforms to the projected reconstruction of the cockset. And here's another example, which is mukta, which, so if you get ta in Maru, you can get a dup or dip. And yeah, it basically tells you that. So you see that here, maybe for Zhu, maybe your phonological history is wrong. Maybe it is a regular lautgesetzlich reflex. And here, of course, what's wrong is not the phonological theory, but you should move it out to create another cockset. Okay. So that's the basic idea of back projecting everywhere, which gives you a lot of context, and we'll take a look at that later also. And so the basic organization of the CAPR workflow is basically what you would expect. So you pre-process the source word list to a kind of computer readable form, and you get the bootstrapping stage where the lexica algorithm generates the first draft of the Cognate assignment, and then you get iterative improvement before deciding that you are going to publish that as a etymological dictionary. So the interesting thing here is the actual iterative improvement. So the idea is that, so basically, since we have this bipartite hypothesis, so you're supposed to, like when you make a better transducer, then it could somehow contribute into the cockset editing process to create better cocksets, and vice versa. So you can have this zigzag. You work on transducers, and then you work on cocksets with new stuff. You feel very happy, and you get your new stuff, and you use that back to create better transducers, and you feel very happy, and yet better, and until you get the final result. So let's talk about this iterative improvement in both parts. So the more interesting part is that of Cognate assignment. So how are you going to solve those seemingly intractable problems of creating cocksets? Well, so here is this misattribution cockset error. And so, well, I put it like this. Since I put it like this, then of course, how are you going to correct them? Dragging them around. Okay, so with back projection, you get a very nice step. Let's just take a look. Oh, okay. Here's a video. So we have this cloudy word that we want to kind of okay. Maybe I shouldn't put it in full screen because there's a part that says not visible. Okay, let's start from the beginning. So yeah, we just looked at this cloudy word, and maybe something doesn't really belong here. So yeah, we're going to working on it. So we create a new cockset. So it's just as easy as dragging the word from the old Cognate to the new Cognate, and take a look at how the reconstruction actually changed. Okay, now we put DAP here. Since DAP doesn't have a reconstruction according to our current theory, so there's no reconstruction for this Cognate. Then we drag the other DAP here. Okay, this one does have a reconstruction, which is deep or dupe. So it is inferred that basically this this new Cognate likely has a reconstruction of deep or dupe. Okay, so that's the basic idea. You allow linguists to drag words around, and you use transducers to provide this most useful kind of context that can be provided to the linguist. Okay. Of course, we just saw that on our board, we just have 3 Cognates, and how that possible? I mean, we have a lot of them. Well, so that's a problem that needs to be looked into very seriously. So here's what we want. So first, partial visibility. The idea is that you shouldn't let yourself like be overwhelmed with this, with the ocean of Cognates. No, it wouldn't work. And so either like you wish to prioritize them, so maybe some are more important, more reliable, or likely to end up in the smaller etymological lexicon or whatever. But if you don't have that, then just give me some random Cognates so that I don't have to work on 30,000 of them at once. The second idea is that of grouping. So since we have this oversplitting or misattribution relation where we really do need the Cognates to be visible to the human eye on the same screen in order for human beings to realize that, okay, maybe we should drag it from here, or maybe we should merge 2 Cognates together. So we need to find a way to group together the Cognates that are likely to have an oversplitting or misattribution relation. Okay, here's what we do. So first, we have a criterion called a reliable Cognate. So the idea is that, well, since in the etymological dictionary, usually a word, netimon, is justified by more than one example. So yeah, at least it wouldn't do us any harm if we just declare that we only want to see the Cognates which already has a reconstruction which is justified by words from more than one language. And the second idea is that of boards. So basically, you take a reliable Cognate, and you try to see if there are other Cognates, reliable or unreliable, that has the same, that can have the same, that can have the same reconstruction. So you make an equivalence class. You just partition the Cognates into different boards, where the boards are those where the Cognates in the boards just share one or more reconstructions. So what does that do? Well, in doing this with transducers, you make only one small part of Cognates visible. And also, since they're visible in boards, every board contains Cognates that are very likely to have an oversplitting or misattribution relation, since some of their words already share a reconstruction. So yeah, they may be very, very, very related. Okay, boards also offers us this task management benefit of chunking it up to manageable bits, so that if we take a look at some lovely boards. Okay, here's a board. Here's a board with a lot of cogsets, but not that a lot. Here's another board. Notice that, for example, here is a cogset that is reconstructed to ban. Here's another, and some of the glosses are all, we all, or whole. So yeah, they should be merged together. Here's a rather large cogset. Sorry, here's a rather large board. We can merge things together. Here's a very good board which contains basically only one etymon. However, there is one word that doesn't look the same, which is this ye. This ye is just a word for water, but the algorithm failed to understand that ye is not the same as the other p words. So let's move it out of it. And here we get a word that is reconstructed as big, and that means to go to battle. So, and here you get the same meaning, but the actual reconstruction, even the superficial form, kind of allows you to make this decision. And of course, to fire short is the related idea to go to battle. So you can merge all those cogsets together. Cool. And let's take a look at, so this is the, I'm not really working here. This is just the results of the first fishing. So it's, you don't have a lot of things here. And yeah. Okay, that's the basic idea of it. So this process of using transducers to put cogsets into visible boards we call fishing. And why do we call it fishing? Because basically with every improvement on the phonological history on the transducers, then two things happen which makes more reliable cogsets visible to us. So if you do a new bad transducer for a new language, or you improve a transducer for a language that already has one, then either more cogsets are judged as reliable, or some little small cogsets actually have a reconstruction and can be attached to another reliable cogset. That's the basic idea. So we have this little nice fish icon to indicate the new cogset that's just got fished up. So here's how the fishing works. So we color code everything in this way. So this gray box represents the results of Lexica algorithm, which is a huge bunch of possible cogsets waiting to be corrected. So somehow I'm being very hand wavy here. You buckle yourself up and put together a rough first draft of historical phonology. And with fishing, you actually fish out a lot of cogsets into this red portion, which I call visible or boarded. Then with the Cognate assignment interface, the one that we just seen a lot of videos of, human linguists can edit the first bunch of boarded cogsets into human curated high quality cogsets. Then you get better hypotheses of historical phonology, and it fish out coxes with these better historical phonology. And you edit them again using the interface. So that's the idea. So with this fishing thing, you basically finally have an incremental kind of way out from the conundrum of too many coxets. Okay, here's an interesting thing that I wish to talk about a bit, the regs, or basically because your first transducers aren't perfect, they are going to pick up some things that with later transducers, the fishing algorithm thinks that they shouldn't belong on the board. So they get assigned this cute dead fish icon. And if we take an actual look at those dead fish things, it's very interesting. So for example, this means tile, like the tile you put on the rooftop of houses. And the first thing you notice that is that they look a little bit too similar for actual cognates. Maybe this should be or maybe that should be oo. But no, they are wa, va, va. And the second thing is that they receive quite disparate reconstructions. So this one is wa with the 0 tone, and this one is wa with the H tone, and this one doesn't have a reconstruction. It isn't inherited looking syllable. So what happens? Of course, if you speak Chinese, you know that it's basically the Chinese word for tile. So so you see basically that by using algorithms and transducers together, it also it also weeds out the learns if you're interested only in the inherited part of the lexicon. Okay, so here's the idea. So we're trying to build an iterative workflow which allow you to work on one of the two parts of the bipartite hypothesis. And yeah, you get transducers. When you get better transducers, it can help you to fish coxes, and also transducers kind of contribute directly to the UI. So you are helped and spoiled by the transducers to create better coxes, which maybe can be used to create better transducers. So some discussion. So this interface and this efficient workflow basically combines the two approaches previously discussed, that of automatic cognate detection and that of back projection etymology. So for the math type, you know, if you do math or physics, you know the idea of like one object degrades into another in an extreme context. So if you imagine that the cognate detection algorithm says that every word is not cognate with every word or with any word, and it's basically degrades into back projection etymology. And yeah, it's basically both, but of course it's the actual combination that is the interesting thing. So it kind of combines the advantages of both methods, especially with regards to the scope of data. So automatic cognate detection algorithms are not very fussy about small imperfections, but on the other hand, it misses non-obvious cognates, the kind that gives you aha. I remember like learning, I think last year, it's really ridiculous that I had learned last year that enough is genug. It's trivial when you think of it, but if you know the historical phonology, but it wouldn't click, and it wouldn't click to the algorithm either. And back projection etymology gives you those ahas, but if there is a little imperfection either in the actual forms or in your version of the historical phonology, then it just it doesn't appear. So on the one hand, we don't want this overfastness making data invisible. But on the other hand, we do want to know if modern reflexes are lautgesetzlich or not. So the CAPR way, by putting the human linguist in the center of this approach, provides both kind of information. So yeah, it gives the kind of information that the algorithms give, and also the kind of information the back projection, really strict, rigorous etymological method give. And then it gives you all this information and it lets you to decide what to do with it. Okay, now let's talk about transducers. So the thing with transducers is that, well, while you can have those like basic stuff, you have the algorithm creating the coxes and you can correct the coxes. For transducers, you need to create things ex nihilo, and which makes the situation quite frustrating. So here's what we want. So first, to create your historical phonology, you need something to work on. You need your words that you think maybe are cognate with each other, and you need a visualization mechanism to give you patterns to make you think about things. And also, since transducers or any kinds of hypothesis of historical phonology are unmanageable, fragile juggernauts, you do need some way to decompose it into discrete tasks of manageable size with instant feedback, so you know you did something good and not bad. Okay. So we work from correspondence patterns. So the old masters of historical phonology, of course, thinks that the correspondence are the real things and the reconstructions, or may call them here restitution, they're not real, they're just some kind of algebraic notation of the real correspondence patterns. Okay, it doesn't really work like this, but it gives us a quite good idea of like its importance in the whole strategy. So in the context that is kind of where we are from, so for the linguistics of China or Southeast Asia or other Sino-Tibetan languages, there's this kind of thing of putting actual attested forms into correspondence pattern tables. So here's an example. So here is the reconstruction of Wang Fu Shi of Proto Miao, and you get this zh proto initial, and so yeah, you get you really get you know, he tries to be exhaustive. You put all those words here, and so you can see that they correspond with each other. And here's a less exhaustive example is Bidayapon reconstructing prototype. So you get 4 legs and 5 words, but the basic idea is the same. Also, here the idea that of marking, of explicitly marking non-regular correspondences. So, for example, here it says that the tone isn't regular. Here it says that the vowel isn't regular. So that's the basic idea. Okay, in the most general case, generating correspondence patterns from coxes is a generally hard problem, because basically to do this kind of patterns, you need alignment, which means that you need to take leche and latte and lapti and le and kind of fit them together into this kind of table, where so you can say that you have Spanish L, which corresponds to Italian L, which corresponds to a Romanian L, which corresponds to French L, and etc. etc. However, first we note that we don't really need the actual, let's say, the actual algebraic expression of the correspondence patterns. So we need them mostly as a visualization tool. So I think we can all argue that nothing which corresponds with T, which corresponds with P, which corresponds with nothing, completely misses the point. And but if you don't look at this, but if you use this thing as a kind of index to generate this kind of China or Southeast Asia kind of complete tables with examples, it makes the pattern extremely clear. So yeah, even if it's nothing to T to P to nothing, which is completely asinine, but we look at this and we get a lot of ideas on where this might come from. Okay, so the actual alignment is not important. And of course, at least for the current incarnation of the CAPR methodology, we're working with monosyllabic languages. So we do a very trivial thing, alignment by phonotactics. So yeah, this is like phonology. This is like a linguistic theory of 1000 AD, and you just divide your syllable into initial, medial, nucleus, coda, and tone. And so, yeah, you for every language, the linguists write a kind of parser which passes those things into the schema. And also the schema is combined this way. So initial means initial plus medial, and then you get medial, and you get rhyme, which is medial plus nucleus plus coda, and you get tone. So yeah, the important thing is that you see this is you don't need to take alignment as some kind of very reified thing, but as a tool to help you to see the actual patterns. Okay, so here's how it works. So, for example, we have those languages. So we're going to study Atsi. The interface is very primitive, but it's me doing the programming, so how can it be otherwise? Okay, so you get the correspondence, you wait a little bit to get the report, and so it gives you a title, chapter titles, initials, rhymes, and you get those rhymes with everywhere you get the actual tested forms and also the back projections. Let's turn 2 languages into 3 languages. So we'll still need to wait a little bit to get the actual results. Here they are. Okay, let's look at rhymes again. There is absolutely no interface, so yeah, you just search around in this document. Okay, so yeah, here is a tone correspondence. Okay, that's the basic idea. And with back projection, here's a really great example of how back projection really helps you in reconstructing stuff. So, for example, we see this correspondence pattern. So, zh in Chang Chuan and Xiandao corresponds to v in Ati and r in Maru. So, for example, for chicken, cock, hen, all the same thing, but yeah, they should be merged together. But yeah, there are basically 2 examples. And so for bark, it's grap and vap and re, and this one is groa, vo, and ro. So yeah, when you just take a look at this, then je, ve, and re, of course, it's really difficult to think of any hypothesis that can explain them. But of course, you don't need to do that. So the idea is to enable you to do this gradual refining when you create a hypothesis on the largest, the most regular stuff. And what did that give you? Well, after you created them and you take a look here, okay, so basically it's very clear, easy to see that you have a grouping which makes Achang and Xiandao have a gzh, while have a proto-language gr, while Atsi and Maru have proto-language r. So yeah, basically for those two words and probably others, you get a gr in some languages and a r in some other languages, and you can like make more sophisticated hypotheses from here. So yeah, this is marvelous because, like in the real world, you need to basically maybe someone reconstructs a bad proto-Burmish, and you read this article and you write another article saying that okay, no, how are you so stupid and missing this obvious correspondence pattern, but of course, when your whole mind is taken by those kind of very basic laborious work of collecting correspondence pattern, you can't really see that. And here you can really evolve the hypothesis in a very effortless manner. Okay, so the next problem is debugging. So yeah, you have ordered sound changes, you have fadings and bleedings and whatever. So yeah, it's like the Chinese saying, you make a change to one piece and the whole thing moves. So yeah, this in itself would be very difficult. So the idea is to factor the whole change into tiny atomic changes and in a comparative manner. Okay, so I think it's clearer with an example. So let's continue our video. So we're still studying Ati, Bola, and Maru, and now I'm looking for those cross marks. Those cross marks mean, say that, for example, the Nop word here doesn't even, cannot come from a Proto-Burmish etymon, according to the present theory of the historical phonology of Maru. So yeah, I'll be looking for those kind of things. Yeah, I look for crosses. And here's a good one. Okay, so if you look at it, then there are two crosses here. So you have a whole correspondence pattern for which the current theory doesn't work for any of the forms. So for far and for rely, the Maru form does not correspond, the actual aesthetic Maru form doesn't correspond to anything. And for to measure, it corresponds to something, but you see in every other language is scare. Why is squee here? It's impossible. So here is a problem. So what's the problem here? You see, you have this air vowel in Proto-Burmish, which gives a in Atsi and e in Bola. It's the same vowel. It's the same vowel everywhere in Atsi and Bola, a and e. However, in Maru, sometimes it's e and sometimes it's a. So earlier we have like forgotten, we didn't see that some of the air vowels could become a. And what's the condition? Okay, so de, be, sh, ne, and v, g, ng. Okay, here is it. So basically, you have velars and v. Well, v is I think the sound change from Proto-Burmish word to Maru v could be quite recent. So yeah, the idea is that maybe the Proto-Burmish vowel e changes into r after velars, including the labial-velar approximant. Okay, now we found our problem. So for demonstration purposes, I start with inventing a very bad solution. So here's a bad solution. So first, here's the sound law. That changes A into R mechanically without taking into account the phonetic conditioning. Also, the placement of the sound law is wrong. The sound change is wrong. So you get A to R here, but here is an already existing example in Maru, an existing sound change in Maru where R changes into O. So of course we can predict that our bad version changes A into R, which then gets changes into O, which is not what we want. Okay. So what we get, well, for the words that we're actually interested about, we get nothing. So what did not have a reconstruction? So for example, far doesn't have an English now neither. So yeah, the only difference is that it was the theoretical reconstruction was there, but the current theoretical reconstruction is vor. Both are wrong. However, and here we see the beauty of the CAPR interface. So yeah, basically you have two rows. The first row corresponds to the old transducer, and the second row corresponds to the new transducer. And it checks if your new transducer actually explains the current forms better or worse than the old transducer. In this case, it's worse, and you get, and of course, since it's a systematic degradation of the quality of the hypothesis, you get a huge swath of red with frowning faces across a whole correspondence pattern, which is CAPR's way of telling you that something went terribly wrong. Okay, so now we are reminded of our historical linguistic 101 and the idea that, well, sound laws have consequences. And so we have, so we put it into a better place. And we get these smiley faces telling us that, okay, now the actual attested form va is properly reconstructed to the pan-Burmish etymon where, hooray. However, of course, you still get this huge swath of red, sad stuff. Okay, now we are going to do things seriously. So we remember that it goes after velars. So what are the velars? KG, and we remember there is this W and maybe aspiration. So yeah, it happens after velars. And wonderful. So yeah, we have, okay, what happened? Gosh, okay. So yeah, it did it right for far and measure, but not for rely. Why? Because of course, yeah, rely has this ng, and yeah, you see, yeah, I meant to do this thing wrong in the beginning for demonstration purposes, but now it caught me actually in an actual error. So okay, here's the right version of the sound law. G, g, ng. We finally got the ng. And okay. Okay, so yeah. And yeah, I should feel very happy about this this kind of thing, because when you get like a whole correspondence pattern with smiley faces in green, then yeah, then it's a new situation, a new sound change that is now properly accounted where it wasn't before. However, we still need to change. We still need to check if it doesn't make anything worse. So you do okay, because it's very bad. I type the frowny face into search, and search tells me that there is no frowny face in the thing. Okay, so I'm very happy about my new sound law in Bowler, where air changes into R after V does. Okay, so the discussion. So yeah, for the transducer debugging part, well, so first you get this visualization, the China SEST style full word correspondence charts, which provides the necessary and minimal information for generating the correct hypotheses. And the next thing is incrementality. So basically, yeah, it's very dangerous to change transducers. So we have this kind of atomic change, diff and report with smiling and frowning faces, a mini loop, which ensures that if you are going to do a trade-off, you know that you're doing a trade-off, and if you do an improvement, it's an improvement, and if it's not, it's not. And the third thing is iterativity. So yeah, what do cogsets do in this part? Well, when you have better cogsets, you get more examples. For example, I think the reason that we didn't catch this is that there were too few cogsets in the first version of the phishing. So when you have one example, you're not really sure if something needs to be done about it. And also, when they're checked, when they're properly when you get the rubbish out of a computer algorithm generated cogset, you also get less red herrings, and you get just a much clearer picture of the historical phonology. Yeah, so that's basically it. So yeah, we just talked about the transducer debugging as a part of the iterative workflow. So when you get better cogsets, they can generate good correspondence patterns for you to debug your transducers to make improvements, new hypotheses in an iterative and instant feedback way. That's basically it. So yeah, so sorry for this thing being a bit technical, but I think if we're really going to talk about how to make computers actually useful for historical linguistics, we'll need to see from the beginning to the end how you can make this workflow consistent with itself and iterative and stuff. Okay, that's it. And so future directions. Okay, so yeah, we're still working on the current incarnation of the CAPR methodology. So with a view of producing a really good etymological dictionary of Flemish languages, and frankly, I don't program that well. So yeah, but yeah, just an idea. So putting it more seriously, so we see that a lot of things are greatly simplified by the fact that we are working on monosyllabic languages. So basically the thing is that first the alignment problem, which is really hard, is simplified. So in order to address the alignment problem, I think we'll at some point need to make much better transducer engines than the kind of, it's like a pig, it's like Perl regular expressions versus real regular expressions. As long as you have this bidirectionality, I think we should actually explore ways to put more stuff into it. And also, since with monosyllabic languages, we don't really care about like paradigmatic morphology or analogy, which destroys the perfect lautgesetzlich relationship between the inflected form in the daughter language and the inflected form in the source in the proto language. And yeah, first. We need to think about like even encoding them in a rigorous and machine readable and machine verifiable and way is an open problem. So let me end this talk by saying some good words about transducers. So I think at some point with this and other technologies, it can bring us to something that is in French we say démocratisé, which in English is like de-gatekeeped. So for Indo-European linguistics, you get an actual discipline and people work on it. So yeah, so people talk in the laziest, most symbolic way possible. But for them, it's doable. But like for minority languages, we need to be very frank, and I don't think we're getting 300 professors bickering with each other on one tiny language family in the jungles of North Laos. It doesn't work like that. So what we can do is to make our hypothesis transparent and so easy to change and easy to understand, and so a kind of less institutionalized, less intense cooperation could still move us towards a more reputable future for the historical linguistics of world's languages. Okay, that's it. Thank you very much.
Thank you, Xun. Great presentation. We did get a couple questions in chat, but since your colleague Nathan Hill is here with us, so he was able to respond to some of those topics. One was about that question of if you're going to be able to move on to polysyllabic languages with this, which you just addressed a bit. Another one was just on what is the usability of this code for people that don't have a background in coding or computer programming. How accessible is this for historical linguists who want to apply this technology, but you're basically starting at ground zero when it comes to coding?
Okay, let me start on the polysyllabic problem. So for polysyllabic languages, there are things, or like for non-Chinese-ish languages, there are things that are more difficult, but there are also things that are simpler. So, for example, a large problem for our actual Burmish work is that since almost every word is bimorphemic or quadrimorphemic, so the juggling of these parts and stuff around things get much more difficult, and I think that's the reason why Lexstat is supposed to work extremely well, but does not work as well in our Burmish example. So first, is the thing is that like if you take like our favorite example, Polynesian, then as long as something can be done for the alignment that requires less human intervention. Polynesian is in a lot of senses much easier to treat than the kind of monosyllabic Chinese, China or Southeast Asian kind of languages. That's the first point. And the second point is that, okay, so yes, it is very difficult, and yeah, after putting this to something, I'll be quite actively thinking about that. What was the second question?
The other one was about usability for people without coding experience. So are you making the computers useful for people who don't know how to code?
Okay, so let's say the good thing about transducers is that writing transducers is much easier than actually coding. So for anyone that had had experiences like had like a classical generative phonology, yeah, you know the notation, and that's the first thing. And the second thing is that we get this kind of interactive. Okay, so for example, let me talk about myself actually programming. So I know everything about programming, but I can't program very well. However, I do proof assistance quite well. So proof assistance is the kind of thing where you write a new thing and computer checks if your thing is correct and whether it fits into the context. So you get all those like little things that kind of helps you keep track of the details, which is one of the basic ideas of CAPR. And I think yeah, where I don't terribly worry about this. We also get the other part, which is that for any language, for any language group, we will actually have a lot of things that like this, a very clean, user-friendly version of CAPR can solve, and you need a Python. You need to do some Python, but I think we'll need to create some kind of ecosystem where we can help linguists with those kind of more thorny, more ad hoc questions
Xun, may I just say, kind of at a totally practical level, if people want to work on the Burmish languages, there's an extremely easy user interface that's online right now. Yeah, so I can't program at all, and I can use it very well. And this is what Xun showed off, and it works very well. But he has had to do a lot of programming in the back to make this possible, and and he's not, I don't know, we don't have a professional programmer or anything like that. So the back end is probably a little bit kind of shoestring and chewing gum. So if someone wanted to work on it for their own language family and not for Burmish, they would have to do they would have to have some kind of program involved. And they would also have to do the pre-processing to make the data ready for this workflow. But they could start from the code we've had, and then in terms of what Xun was saying, I think that as a discipline, and this is one of the reasons why we want to sort of talk to people, is we can't be the only people who make this thing, right? Because then it will be made for us, and instead, if people can become convinced of it as a conceptual framework and as a methodology, then either they can actually build on the code we've built, or they can do their own, right? And it would be good to have a sort of ecosystem of people working in this way. And then I think the last thing I would say is that Matt's List's group has produced a lot of data that would flow into this system very smoothly. So they have stuff on Bai, they have stuff on Hmongmian, they have stuff on Tucano. So if you happen to be interested in one of those languages, it would be substantially easier to get this system going. Yeah, that's what I wanted to say.
Great. Yeah, so it sounds like there's a bigger concept here that you've sort of showed a proof of, I guess, for one set of languages that you'd like to see grown into other languages. That would require setting up more data sets, more interfaces for people to interact with to make that more usable, but this could potentially be expanded if more people got together around this concept. Do you agree with that, Xun?
Yeah, I think so, and I wish to echo the previous remark of Nathan that that basically it's 2020, and for a lot of languages you get very high quality. For more than that, you get very high quality free online data sets, and yeah, theoretically, CAPR can help you produce those produce very good results from those data sets.
Great. So I think we'll leave the presentation there for now. Then hopefully there will be more conversations as people either contact you about Burmish data or trying to develop this for other language groups as well. Sounds like there's a lot to discuss here. Thank you so much for taking the time to prepare this presentation and share it with us. Definitely, we all learned a lot, and a lot of appreciation in the chat too for the quality of your work and what it means to the field of historical linguistics, especially for these minority languages that are more or less been ignored in the big picture of historical linguistics. So